Consider an example of Thevenin's theorem. Find the Thevenin's and Norton's equivalent for the circuit shown in this figure, with respect to terminals AB, and also determine the current across this load RL. So in this circuit, we have two sources here. One is this voltage source, another one is a current source. And we have to replace this circuit with respect to these terminals AB. The first step is determine the open circuit voltage between these 2 points. This is also called as Thevenin's voltage or open circuit voltage. When we looked at these 2 points, this is 1 ohm. It is an open, so current will not be flowing in this ohm. Hence, whatever the drop across this 12 ohm is this open circuit voltage. To find out the open circuit voltage across this 12 ohm, just I am applying a mesh analysis here. So just I referred two mesh equations. One is X, another one is Y. X and Y, while looking at this Y, we have one current source here, 2 ampere, that opposite of this 2 ampere. And X and Y are the conventional directions, and 2 is opposite to this Y. So Y is simply as a minus 2 ampere. Coming to this first mesh X, mesh equation for this X is, we have two resistors here, 4 and 12. It is 16x, and this 12 ohm, this mesh Y current is also flowing in this, but it is opposite to this X. So that's why minus 12Y, and within this mesh or loop, we have one voltage source of 32. So that is equal to a 32 volt. 16x minus 12 of minus 2, it is a 24. 32, then x is equal to this, simplifying 32 minus 24 by this 16, it is a 0.5 ampere. This is the current. Now I have to determine the drop across this 12. The drop across this current flowing in this. We have two currents here, X and Y, both are in opposite directions. And then drop across this is, with respect to this AB, 12 ohms into X is a 0.5 minus, because opposite, minus of minus 2, because this Y, it is a 0.5 plus 2.5. 12 into 2 point, it is a 30 volt. We have another methods also. By node analysis also, you can determine the open circuit voltage or drop across this 12. Here, there is only one node because no current flows in this ohm. You call it as a V minus 32 divided by 4. This is the one current. Then V by 12, another current. Then one current is coming to this node. That is a minus 2. Simplifying, V by 4, that is a 0.25 V, and 32 by 4 minus 8, V by 12, 0.083 minus 2. In this way, we simplify and determine this is also 30 watt. You can apply node or mesh. So now we ready with the open circuit voltage. Next step is determine the Thevenin's impedance or Thevenin's resistance between these two terminals AB, from these two terminals. To determine the Thevenin's impedance between these two terminals, whenever current source present in the circuit, simply remove this one, and if there is an voltage source, short this one. And now I will redraw this circuit to determine the Thevenin's. So shortened one, now 4 ohm, and this current source I removed. So 12 and 4, these two are parallel in series with the 1 when I look back to this. So 4 into 12 by 16 plus 1, that is 4 ohm. This is the Thevenin's equivalent. And Norton's equivalent, just replace this source with the current in parallel with this Thevenin impedance or Thevenin resistance. 30 by 4, it is 7.5. Last step is determine the current. Load current, connect that load now. Now it is a simpler one. 30 volt, IL is this voltage divided by 4 plus 6 ohm. 30 by, that is a 3 ampere.